Welcome to the lecture series on process integration. This is module 4, lecture number 9. The topic of today's lecture is cost targeting. In this lecture, we will introduce the cost targeting, we will talk about capital cost targeting, then operating cost targeting, and finally, the total cost targeting, which involves the capital cost targeting and operating cost targeting for a hen. The objective of the hen synthesis is to develop a network of counter current heat exchangers that minimizes capital investment and operational costs. When a problem of heat transfer is given, then the quantity of heat transfer is known, and based on this quantity a heat exchanger network has to be designed. Though the quantity is not known exactly, but roughly the quantity is known. Now, we have to develop a heat exchanger network which will have less cost than others, because in pinch analysis a number of heat exchanger networks can be designed to satisfy the operational constraints. But what heat exchanger network we should select? We should select that heat exchanger network which will operate with minimum capital investment and operational cost. To know this, the cost targeting is necessary, because when we design the heat exchanger networks, we have to target its cost, that is capital cost and operational cost, and we will select that heat exchanger network which will have minimum. It leads to the optimization of delta T minimum, which will offer trade off between the capital cost and the energy cost. It needs a lot of discussion. We have seen that a heat exchanger network is designed for a certain delta T minimum, and what delta T minimum we should take for the design of the heat exchanger network. We have seen that in the problems we have assumed the delta T minimum. The question is whether the assumed delta T minimum is correct or not. So, what is being done, that for different delta T minimum hens are designed, and then cost targeting of those hens are done. Then we find that at a certain value of delta T minimum, which is called delta T minimum optimum, the TAG, which is total annual cost of the heat exchanger network, is minimum, and that delta T minimum optimum is considered. And optimum delta T minimum, the total annual cost TAG of the hen gets minimized. The TAG of a hen for a given delta T minimum is found out using cost targeting. Now, let us see about the capital cost targeting of similar materials of construction. Now, we can divide the cost targeting into two parts. When the hen is made up of similar materials of construction, that means if all the heat exchangers in the heat exchanger network are say made up of mild steel, then cost targeting will be differently done. But when the materials differ, that means some materials are of say stainless steel, other materials are of titanium, other materials of MS. So, if the materials change or the design changes, that means some heat exchangers are for high pressure, some are for low pressure, then capital cost targeting will be done in different way. In this lecture, we will see both the ways of cost targeting. Now, to start with, we will do cost targeting for similar materials of construction. The cost of a heat exchanger depends primarily on its material of construction, pressure rating and the type of heat exchanger itself. The cost of a single heat exchanger with surface area A can be found out using simple relationship. Installed cost of the heat exchanger is equal to A plus B A to the power C, where A is the area of the heat exchanger. The above equation A, B and C are the cost law constants that vary according to the material of construction, pressure rating and type of heat exchanger. The distribution of the target area between network exchanger is unknown while doing the cost targeting. What it tells that if we are designing a hen and say 10 number of heat exchangers are there in the hen, it is difficult to say that all the 10 heat exchangers will have equal area, they will have different areas, and hence this problem many a times creates problem in capital cost targeting, because the equation which we have used A plus B A to the power C works well in a narrow range of area. Therefore, using previous equation to find the capital cost of a heat exchanger network consisting of many heat exchangers, the assumption is taken of equal area of all the heat exchangers. So, what is basically done? The network capital cost, that means heat exchanger network capital cost, is equal to number of units in the brackets A plus B A network divided by n to the power C, where A network means the area of all the heat exchangers summed together in the network, and n is the number of units in that network, that means number of heat exchangers in that network or number of cells in that network, whichever is appropriate. We have already conducted the units target and cells target. So, from the units target the value of n is known, and from the cells target the value of total cells available in the heat exchanger network is known. So, it is not difficult to find out n value. The above equation is valid if the problem is dominated by equipment with a single specification, that is material of construction, pressure rating and equipment type. So, this is the drawback of this equation of capital cost targeting, and if somehow the material of construction, pressure ratings and equipment types are changing, then this equation will give error. The basic area targeting algorithm, the Bath algorithm, gives the true minimum network area if all the streams have the same heat transfer coefficient, and slightly above the minimum if the heat transfer coefficients varies by less than an order of magnitude, that is 10%. We have gone through the area targeting procedure. There we have used Bath algorithm. The Bath algorithm will give minimum area of the heat exchanger network if the heat transfer coefficients of the streams are almost equal or slightly changing within a error margin of say 10%. However, this does not result in 10% error in capital cost targeting, as the practical designs are invariably above the minimum. If the heat transfer coefficients are changing, are not within a band of 10% or so, the area offered by the Bath algorithm will be higher. And so, in most of the area targeting, the area which we find out is more than the minimum area. There are two inherent errors in this approach of capital cost targeting. The total heat exchanger area is assumed to be divided equally between the exchanges. This tends to overestimate the capital cost. And the second problem is that the area target is slightly less than the area observed in design. Now, we will see that when we are targeting a area of a heat exchanger network, this is the minimum area which we are targeting. But when we design, we find that the total area of the design is little bit more than the minimum area which we have targeted by area targeting method. So, area targeting method gives the bottom line. However, when we design, then we are above this bottom line, and hence some errors will creep into this equation. As mentioned earlier, cost is involved at two places in any heat exchanger network synthesis problem. The first cost is capital cost of the heat exchanger, heaters and coolers. When we design the heat exchangers which exchanges process to process heat, then there is a cost involved in the manufacturing of these heat exchangers, heaters and coolers, and that cost is called capital cost. Once we design and manufacture the heat exchanger, its operating life is many years, say 10 years or so. So, the capital cost which we are investing, it is for a longer duration and it is for a duration of the operating life of the heat exchanger. The another cost is utility cost. In a heat exchanger network, we will be using utilities, hot utilities and cold utilities, and the consumption is continuous. So, a cost is also involved in purchasing those utilities or handling those utilities. With the change in driving force delta T minimum, there are two costs very opposite to each other. As I have already told you that the area is a function of delta T minimum, that means area of the heat exchanger network is a function of delta T minimum. So, when we change delta T minimum, we have to see that what is the trend in change in the capital cost and what is the trend in change in the utility cost. We will see that both costs vary opposite to each other. If it is so, then it is a perfect case of optimizations. That means, a delta T minimum optimum will be available, which will give me the minimum total annual cost of the heat exchanger network. With increase in delta T minimum, the utility cost increases as the utility consumption increases. This we have already seen in energy targeting, that if I increase delta T minimum, the amount of hot utilities as well as cold utilities will increase, and hence the utility consumption will increase. However, the capital cost decreases as the area of the heat exchanger network will decrease due to the increase in driving force. We know there is a equation which tells Q equal to U A delta T ln, and this clearly tells that if I increase the delta T minimum, then the driving force for heat transfer increases, and hence it will require lower amount of area to transfer the same amount of Q. Thus, it is better to consider both the cost during targeting a heat exchanger network for the further determination of optimum delta T minimum using super targeting. When we optimize delta T minimum as a function of TAC, then this process is called super targeting. The capital cost or fixed cost and operating cost, which is a utility cost, or it is a pumping cost, or a mixed of these two, are expressed in different time scales. This is very important. The fixed cost is expressed for the full operating life of the heat exchanger, whereas the operating cost is expressed on yearly basis. So, the time scales are different, and hence we cannot add them. For example, the capital cost is expressed for the operating useful life period of the heat exchanger, whereas the operating cost is generally expressed per year basis. Therefore, it is necessary to find a common time scale for joining these two costs. And what will be that common time frame? This is done by determining the annualized capital cost, and the annualized capital cost is expressing the capital cost per year basis before it is added to operating cost to make the time scale consistent. The annualized capital cost is equal to capital cost into I into in brackets 1 plus I to the power n divided by in brackets 1 plus I to the power n minus 1. So, this is the factor which has to be multiplied with the capital cost to convert the capital cost to annualized capital cost. So, the total annual cost TAC is equal to annualized capital cost plus annual utility cost. So, here we have added both the cost, that is capital cost and utility cost, to form a factor which is called total annual cost. Here the I is the fractional interest rate per year and n is the number of years, that is the useful life of the exchanger in years. Now, let us take a problem and demonstrate this. The process shows in the table below. Pure counter current 1 cell and tube heat exchangers used, and delta T minimum is taken to be 10 degree. Now, the problem shows that there are 3 hot streams and 2 cold streams, one steam as hot utility and the other cooling water as cold utility, and the heat transfer coefficients are also given for each stream. Now, the aim of this is to calculate the capital cost target of the individual heat exchangers using the heat exchanger capital cost expression, which is 30,000 plus 400 into a to the power 0.9. So, such type of equations we will find where the constant 30,000, 400 and 0.9 are the functions of the specification of the heat exchanger, where A is the heat transfer area in meter square and to calculate the TAC we should have also the operating cost figures. The utility costs are given below. The steam cost $120,000 per megawatt per year and the cooling water cost $10,000 per megawatt per year, and I is 10% and N is 5 years. N 5 means the operating life of the heat exchangers we are choosing is 5 years. Now, if all these data are known, we can do the area targeting. So, the first part will do the area targeting, and based on the area targeting we will have a area of the heat exchanger network, and that area will be used to find out the capital cost of the heat exchanger network. Once the area of N is known, its capital cost and annualized capital cost can be computed. Using problem table analysis PTA, one can do energy targeting and subsequently can compute the cost of utility per year. So, utility cost will be known through area targeting, the capital cost or the annualized capital cost will be known. Once these two part of the costs are known, we can find out the total annual cost TAC by adding the annualized capital cost with the utility cost. Now, if you do the PTA analysis of the stream table which is given to us, then we find that the minimum hot utility requirement is 1064.52 kilowatt, minimum cold utility requirement is 855.84 kilowatt, and CP values of hot and cold utilities are calculated as follow. Now, for hot utilities we have calculated this is 1064.52 kilowatt per degree centigrade, and the cold utilities is 21.396 kilowatt per degree centigrade. For the hot utility calculation, we will see that we have taken the delta T is equal to 1. That means, the steam condenses within a range that is 300 to 299. Why we have taken 1 degree centigrade, I have already explained in many lectures, and that is why I am not explaining here. Now, what is our aim? Our aim is to find out the total heat exchange area of the network, and we know that to do this we have to plot the balanced hot composite curve and balanced cold composite curve, because in this area of the heat exchanger network area of the heaters and coolers are included, and for that it is necessary that the composite curve should have hot utility and cold utility. So, when we plot the hot utility and cold utility with the composite curve, it converts into a balanced composite curve. So, here we have plotted the streams. The H 1 moves from 159 to 77, its Cp value is 22.85. H 2 moves from 267 to 80, its Cp value is 2.4, and so on and so forth. So, we have taken all the hot streams from the stream table and we have plotted this. Then we have calculated the summation Cp value for the hot streams. In the first interval, that is 80 to 77, only H 1 stream is operating and its Cp value is 22.85, and hence here this is entered 22.85. But however, in the range of temperatures, that is 90 to 80, there are two streams H 1 as well as H 2 streams. So, we have added the Cp values of both. So, it becomes 22.85 plus 2.04, which comes out to be 24.89. So, in this manner we have computed the summation of Cp values here in this column. Then we have to calculate the QHB values. This is calculated as the delta T, which is 3 degree here from this level to this level, into this Cp value. So, it comes out to be 68.55, and for this the delta T is 10 and summation of the Cp value is 24.89. So, 24.89 into 10 is 248.9. So, similarly, all these values are tabulated here. Then we calculate the cumulative Q values, which is for the first interval this is 68.5, for the second this is 68.55 plus 248.9, which comes out to be 317.45. In a similar manner we have calculated the cumulative values. Let us see how to plot the balanced composite curve. For this purpose, we first draw the temperature levels and then find out the cold streams and cold utility. Here the cold utility is working from 20 degree centigrade to 60 degree centigrade. The cold stream C1 is operating from 26 to 127 degree centigrade, and C2 is operating from 60 to 265 degree centigrades, and they have the MCP values for C2 is 19.61, C1 is 9.33 and Cw, that is cooled water, is 21.396. And then we find out what are the summation of Cp values. Now, in this temperature range 26 to 20, only cold water is working and its MCP value is 21.396. So, here we will have 21.396. Similarly, in this temperature range 60 to 26, two cold streams are working, this cold water and C1. The summation of their Cp values is 21.396 plus 9.33, it comes out to be 30.726. So, in the similarly we have filled up this. Now, this Q value is computed by multiplying the this temperature gap, that is 26 to 26 into 21.396 is 28.376, and similarly we have calculated the QH values and filled it up. And in the cumulative, so this is in this level it is 128.376, and for this is this plus this comes out to be this value 1173.06. Similarly, we have computed the cumulative values. Now, we are ready to plot the balanced hot composite curve and balanced cold composite curve, which is BCCC. The enthalpy values at different temperatures are known to us. This we have already computed for hot balanced composite curve and cold balanced composite curve. So, based on the cumulative Q values and temperature levels for the cold balanced cold composite curve, we have first plotted the points and then we have joined them. So, this one shows the balanced cold composite curve in which the cold utility is included. Now, we can plot the balanced hot composite curve. For that we will first plot the points and then we will join. So, we have joined this is the balanced hot composite curve and this is the balanced cold composite curve. Now, we will see that there are places where the temperature is known for balanced hot composite curve, but it is not known for cold composite curve, and so on and so forth. Here we see that here this temperature is known for balanced cold composite curve, but the corresponding temperature T H 3 is not known for hot composite curve. Why this is necessary? Because when I segment this balanced cold composite curves into different enthalpy intervals, then say I take into account this enthalpy interval, to find area I should know this temperature, this temperature, this temperature and this temperature. In this case, this temperature T C 4 is not known and T H 5 is not known. Unless and otherwise I find out these two temperatures, I cannot find out the LMTD log mean temperature difference for this enthalpy interval. So, if it is the LMTD is not known, I cannot find out the area for this interval, enthalpy interval. And to find out the total area of the heat exchanger network, I have to find out the area of each enthalpy interval and then sum them together to find out the area of the total BCC and BSCC and CHCC curve. So, we will see that how to compute the unknown temperatures. So, example we will take here itself. Now, this is the equation. I am interested in finding out the T C 10 temperature, which is here at this point. T C 10 temperature is there. So, we see that this is a straight line. So, we can always apply the straight line interpolation rules or linear interpolations rule, which is nothing but this equation for this case. So, here T C 12 minus T C 10 is equal to summation of C P C B here, which is 19.61, the summation of this, the streams which are present here. Now, and then this is equal to the enthalpy available here, which is this, and the enthalpy available here, which is this. So, if we use this equation, we compute the value of T C 10 as 198.64 degree centigrade. Now, in the table, if we compute this, we find that this T H 3 value is not known. It is using this 4 values to compute the value of T H 4, T H 3. Similarly, if you want to find out T C 10, which was shown in the example, it will be using this 4 values to compute the value of T C 10. So, similarly, the all unknown temperatures here in the cold composite curve or in the hot balanced composite curve can be computed and filled up. These are the equations which are given for computation of this. We have explained clearly, and here it gives you the value of the different unknown temperatures of the balanced hot composite curve. This we have already demonstrated in the area targeting. Similarly, we can find out the unknown temperatures of the balanced cold composite curve. Now, this shows that we have computed all the temperatures required, including the unknown temperatures of the balanced hot composite curve and all the temperatures required, including the unknown temperatures of the balanced cold composite curve. Now, the most of the data is available to compute the area of the different enthalpy intervals. So, we here compute the Cp by H, summation Cp by H for the balanced hot composite curve and Cp by H for the balanced cold composite curve. And this we have computed. So, here we compute summation Q by H, which is for this first interval. So, this is the temperature difference into the value 228.5 plus 23.20 minus 20, this is taken from here, into this value, which is the summation of Cp by H. So, it comes out to be 1028. So, this includes the heat available with the hot streams in that temperature interval and the cold streams as well. So, similarly, we compute for all other enthalpy intervals. Then we compute the LMTD. So, for LMTD, this temperature, this temperature, this temperature and this temperature will be used. So, we now compute the all LMTD factors. Now, the area of a temperature interval is given the summation by Q by H value for that interval divided by the LMTD of that interval. So, we have this value known, we have this value known. What we have to do is divide this to this and find out the area. So, these are the area values. And when we sum the area, it comes to be 41546.659. So, we compute the cost of the capital cost based on the area which we have calculated, and then we convert it into the annualized capital cost by multiplying with this factor, which comes out to be 198465.47 per year. So, area was this, capital cost, we have used this equation for the computation of capital cost, we used capital cost here and then converted, multiplied by with this factor to convert it into annualized capital cost. Now, the operating cost is hot utility cost plus cold utility cost. So, this is the amount of hot utility multiplied by the cost of the utility, it comes out to be this. Please remember that this is in megawatt and this is in kilowatt. So, obviously, it has to be divided by 1000. Similarly, the cost of the cold utility is computed using this. So, these are per years and annualized cost is also per year. So, we can add them up. So, total cost of targeting is this plus this. This is the annualized fixed capital cost, this is the operating cost. So, the cost is this total cost, which is called TAC. And then thank you.